Hello, my name is Koen Verhaege. I'm from Sofics. Today I will present you FinFET and FDSOI Solutions for ESD and Analog IOs. First, an introduction on Sofics. Sofics is an IP provider that provides on-chip ESD solutions. And we are focusing to provide you three important benefits. First of all, we want to enable and maximize the performance in normal operation of your integrated circuit. Secondly, we try to enable applications in very harsh environments. And thirdly, we offer you first-time right solutions in a smaller silicon area. To date, we have more than 100 licensees, companies big and small, all corners of the world. And this leads, on average, to one new IC release for mass production every single working day. This means that up to date, about 4,500 ICs, and we're still counting, are being released using Sofics solutions. This is the outline of my presentation. It'll focus on FinFET, 16 nanometer down to 5 nanometer, and FDSOI, 22 nanometer. We will review the technology challenges, suggest and offer you solutions, and support that with data. So what are the application challenges for these advanced technologies? Typically, we see three things coming back. First of all, the need for very high speed interfaces, which translates for the ESD solutions into a requirement that the parasitic load capacitance shall be in the femtofarad range. Secondly, the need for interfacing with legacy systems requires an overvoltage or high voltage tolerant I/O. It means that we have to use lower voltage transistors to build interfaces with, for instance, 3.3 volt, 2.5 volt, and 1.8 volt signals. And thirdly, a typical requirement is one for low power or low leakage, which translates into the ESD requirement that we should not add more than picoamp leakage for the proper ESD protection. And we also should keep the leakage significantly low across temperature range. Here are the technology challenges depicted. On the left-hand side, we see a red curve. The red curve is basically the declining breakdown voltage of the thin gate oxides in the technologies as the nodes are becoming smaller. What we also see is that the supply voltage for smaller technology nodes is decreasing as well. And the distance between that blue curve and the red curve we can call the ESD design window, because it actually depicts the area or a distance that an ESD protection device shall be operating in. And we can see that that window is becoming smaller and smaller. For example, if we're looking at a 0.8 volt FDSOI or FinFET domain, then we see a maximum of 3 volts to operate for the ESD device. It's further worsened by the trend that the metal thickness for the thinner metals as technology nodes are decreasing is also decreasing, which means that the resistance is increasing. Higher resistance for the same ESD current, because the external thread is still the same, leads to a higher voltage drop, and as I just depicted here, that voltage drop should be smaller and smaller as technologies are scaling down. Put it a little bit differently, we can look at this particular very popular ESD protection approach. It is called the dual diode. It basically means that an ESD stress applied, for instance, to a input or output pin is diverted through two diodes to the supply lines. And in the case of a positive stress, a diode up will be used. In case of a negative stress, the diode down will be used in this particular case. What we see is that the total path for the ESD current, and so the total voltage drop, is consisting of the voltage drop across one diode, 2 times metal resistance in the buses, and an ESD protection device or a mechanism that is provided between the power lines. The sum of those voltages is presented to the sensitive node that we are trying to protect. It shall be obvious that as all elements have an increased resistance and the sensitivity of the protected nodes is higher, that we do see a growing challenge to meet that requirement of non-failure of the protected device. Obviously, in different scenarios, a different strategy will be needed. We will not only have to look at the lowest possible dynamic resistance of the clamps, but also we'll have to consider other approaches as will be introduced next. Now, what are the further ESD design challenges in these technologies? Well, one of the important things is the realization that traditional MOS solutions can typically not adequately self-protect themselves. In the FinFET case, I'm showing you here on the left-hand side a classic TLP curve, which is voltage versus current for transient waveforms. And you can see that the performance is very, very low. What we actually see in many FinFET technologies is that the MOS device will fail at the moment that it will go into so-called snapback at very low current levels. Looking at the FDSOI situation, the main concern is leakage. If we only look at the TLP curves, voltage versus current, we see curves that we might interpret as reasonably okay to build ESD protection devices. This red curve over here is using a PMOS device. These other three curves here are using an NMOS device. However, if we have a deeper look at the leakage, which is depicted here, we see a disturbing trend. Have a look at this here. Please follow my pointer here. What you can see is that for the initial stress to the device, we see a slightly increasing of the leakage. There is probably and most likely a physical change here in the devices, which is a reliability concern. So we should not lightly use these devices as the ESD protection devices. These should be further investigated if you want to use an NMOS device in FDSOI as for ESD protection. So, what is a good or better solution strategy or even necessary strategy to resolve these issues in these advanced technologies? Well, we have to look at what we call local clamps, replacing the dual diode approach, such that all of the stress between signal lines and power lines can be handled by a local protection device, which should obviously be very small in area, have very low on resistance, and also add very little capacitance and leakage to the signal node. All necessary to protect the functionality of the sensitive node, but also to protect the physical integrity of the to be protected node. Obviously, we also need power clamps that are very low resistive and effective, because obviously stress can also be applied directly between the upper and the lower power line. When we look at the SOFIX portfolio of solutions, you will find mostly SER-based clamps, silicon-controlled rectifiers. I stress mostly because not all of the solutions are SER-based, but a lot. This portfolio has been proven across a very broad range of technology nodes, all the way down to 5 nanometer. And they have been specifically adapted in layout and design for SOI technologies and also FinFET technologies. Now, an SER, silicon-controlled rectifier, could be represented here by a simplified schematic, basically coupling a PNP with an NPN device. But when looking at the SOFIX portfolio, we're not talking about these plain vanilla SER devices. We are talking about devices that have been engineered with the addition or let's say the addition of control elements and different elements inserted at different nodes of the SER device in order to achieve a working and highly efficient ESD protection device. The result, and I will show you some data of that in the next slides, is that the solution portfolio that we're presenting here is DRC clean, has fast triggering, offers very low leakage, is latch-up safe, is fully compatible with the PDK, and does not require a process change. So, it's time to show you some data. I'll start with demonstrating you the robustness, benchmark the leakage versus the PDK or traditional solutions, and then also offer you the CDM assessment. FinFET ESD robustness is available. That's a statement that is true. Here I'm showing you an example for a 1.8 volt power clamp, can also be used as a local clamp. I'm showing you TLP IV curves, which means voltage versus current, 100 nanosecond pulses. In this particular case, we see a performance of exceeding 1 amp, a leakage that is very low, 400 picoamps at 1.8 volt, an area that is very attractive, 625 square micron, and a scalable performance. Let's look at FDSOI. I'm showing you some more data. I'm not only showing you here the classic TLP curve with the 100 nanosecond pulses, which correlates very well with the human body model performance, but also I'm showing you the VFTLP curves, which are square pulses of 5 nanosecond duration and much faster rise time. What you can see is 1.5 amps of TLP current, not the 2 amps that you might want to derive from the leakage curve. And that is because I've plotted here the red zone for the HBM related core damage, which means that if you use this particular device for the protection of a thin gate oxide transistor directly with the gate dielectric exposed to the ESD stress, then the maximum voltage in transient mode cannot be more than 4 volts, leading to a performance here in this case of 1.5 amp. This translates into a 2 kilovolt HBM performance. The 3.5 amp VFTLP curve, VFTLP performance translates to a 300 volt CDM clamp capability in a 1500 square millimeter BGA package. Note the leakage that is very low. At room temperature, 20 picoamps. At elevated temperature, 10 nanoamps. The area is also very useful and viable for local protection, 715 square microns. Let's look at the leakage. Let's benchmark the SOFIX ESD solutions in terms of leakage versus the standard solutions. Complicated curve, but let me walk you through it. On the left-hand side, I'm showing you data for room temperature, 25 degrees C. On the right-hand side, I'm showing you data for 125 degrees C. We are showing the leakage for clamps that have been designed for 2 kilovolt HBM performance. The blue curves are the SOFIX designs according to the SOFIX design rules and guidelines with the SOFIX devices for 2 kV. The red curves are from designs that are created for 2 kV according to the PDK guidelines. So we're really trying to make an apple-to-apple comparison here. We have normalized the leakage. So value number 1 is for the second FinFET process that we are considering here. This is value 1 for room temperature, and this is value 1 for elevated temperature. I haven't mentioned yet, but you see results for 3 different FinFET processes here, from the more advanced to the less advanced node. What you can see is results for both the low voltage domain protection and the high voltage domain protection in the relevant technology. You can see that comparing the red curves with the blue curves, that there is a distance of 2 to 3 orders of magnitude between those 2 sets of solutions. Basically demonstrating to you there is this benefit of 2 to 3 orders of magnitude less leakage by using SOFIX clamps. And there are many applications where this is a discriminating and very important difference. Let's have a look at FDSOI. I'm showing you here absolute values. So picoamp, nanoamp, microamp range. I'm showing you again results for 25 degrees C and 125 degrees C. Let's focus on the blue versus the red curves. The red results here are SOFIX devices, the blue curves are PDK devices for 0.8 volt in this particular FDSOI technology. over the range of the normal signal operation. And you can see that both for the room temperature and the elevator temperature, the difference in leakage is 3 orders of magnitude. Now, let's have a look at the CDN performance of these devices. What I'm showing you here is VFTLP and TLP data for FinFET power clamps. And I'm showing you the results in one and the same graph for 0.8, 1.8, and 3-volt clamps. The little bit darker lines are TLP curves. The little thinner lines are VFTLP curves. And you can see here the different 0.8, 1.8, and 3.3 volt solutions. The TLP curves and the TLP performance correspond to more than 3000 volts HBM and more than 250 volts CDM clamp capability in a 1500 square millimeter BGA package. And the solutions have also been demonstrated to be scalable. FDSOI. Again, the same story, VFTLP and TLP. The darker curves TLP, the lighter curves VFTLP. The performance obviously scales as well with the pulse width. Power clamps for 0.8, 1.2 to 1.8 volt, and 3.3 volt clamps. More than 2000 volts, 2500 volts HBM, more than 200 volts CDM clamp capability in a 1500 square millimeter BGA package. Again, very scalable. Let me show you some more data. This is a detail of the VFTLP measurement of a power clamp 3.3 volt in FinFET technology. You can see the classic VFTLP curve. And we have looked at the trigger points, right before trigger, right after trigger, the point of 2.5 amps and the point at 4.5 amps. What I'm actually showing you new here are these curves. These are the transient curves, transient current and transient voltage. This over here on the bottom are the input of the test. They're basically the square current pulses. The red one right before corresponds to this point over here, right before triggering. The light blue one or greenish blue one for right after triggering. We see the purple one at 2.5 amps, and we see the green one at 4.5 amps. Above here, you see the voltage transient for the same. Now, these are very particularly interesting because they tell you a lot about the triggering speed. And also they teach you a little bit on how these curves are made. Just for educational purpose, this curve over here is built point by point by averaging out for each stress level that we are applying, and the stress level is red over here, point by point plotting the voltage response, which is taken as the average of the tail part of the transient. You can see that the difference between red and greenish blue over here is prior to triggering and triggering. You can see that the triggering happens without any overshoot and that the duration before triggering occurs is very limited. Over here, the purple and the green curve, we can see that there is a slight overshoot. However, it is not dramatic and it is very limited in time. The reason why I can say that this is not dramatic is that these particular test structures are actually tested with not only the power clamp but also a parallel gate monitor device or a thin gate oxide transistor that is placed in parallel with the clamp that is directly exposed to the same ESD stress as the power clamp. And as that gate monitor did not fail, did not get damaged in this test until the damage of the device, we know that the protection has been triggering adequately and in time to protect. Now remember this curve because I'm going to refer back to it later on. Here, what we are seeing is standard, well, first of all, it's FDSOI, and here we are comparing a standard SCR with an enhanced SCR. Remember that in one of the few earlier slides, I did mention that you cannot just use a plain vanilla silicon controlled rectifier, but there's a lot of techniques and things that need to be done in order to build a proper SCR device for ESD protection. And you can see why in this one. The standard SCR is represented by the green curves, and these full line curves here are the classic VFT pulses or measurements. The dotted lines, they are constructed not from the average of the tail of the transient that I showed you on the last slide, but from the peak value from the transients. And obviously these are higher. And what you can see here, if you use a standard SCR without the proper techniques to enhance its trigger speed, there is a big difference between the average of the tail and the peak value that you can record. This is dramatic and non-functional. This is good and working as proven by the experiments with the parallel gate monitor. Here are my conclusions. I did present to you the intrinsic challenges of deep nano FDSOI and FinFET technologies. Basically, I have explained to you the narrow ESD design window that limits the options for ESD protection, and I have indicated how we can address that. I think I have proven to you that there is IP available for all interfaces and supply lines in these technologies. They are silicon proven and scalable. They provide solutions for high-speed digital and high-frequency analog IOs. There are solutions available for low power, low leakage. I have demonstrated to you 2 to 3 orders of magnitude improvement. And also very important, the solutions are standard process compatible. They are DRC clean, latch-up safe, and also robust for CDM stress. A final overview is given here. The solutions are available for all interfaces and supply lines. In addition to power clamps, there are also a group of local clamps that are available. The difference between the PDK and the SOFIX Portfolio is that in addition to the dual diode and power clamp scheme that is available in the PDK, the SOFIX solutions offer semi and full local protection, secondary protection solutions, and also full local and secondary protection designs. In terms of I/O coverage, obviously both PDK and SOFIX cover the standard I/O requirements, but in addition, in the SOFIX Portfolio, you will find solutions for over and under voltage tolerance, for I/Os with core transistors, for ultra-low leakage and ultra-low capacitance solutions. Well, thank you very much for your attention. You can find more information about SOFIX on our website www.sofix.com. And you can also find the contact information there for our regional representatives. You can always contact my colleague Bart Keppens, his email address bkeppens@sofix.com, or you can contact myself, Koen Verhaege, the presenter of this presentation. If you would like to learn more about SOFIX, there are 3 40-second videos that are available on YouTube, and you can assess them through scanning one of these QR codes over here. Thank you very much for your attention, and have a very nice day.